Hello everyone, in this video we are continuing class 11 chemistry, chapter 4 chemical bonding and molecular structure. Under that we are doing bond parameters. This is part 2. Under part 1 we have already done bond length. In this video we will do 3 bond parameters or 3 bond features, namely bond angle, bond enthalpy and bond order. Before we continue, please watch the video completely so that you get all points cleared. And if you think the video is useful, consider subscribing my channel. Press the bell button and all button for notification of more videos like this. Do not forget to like and leave your comments in the comment box below. Thank you very much. I am Anandavalli. I welcome you to this new video from Guidance Education channel. Okay, now we will start the class. First we will take up bond angle. This is the second parameter. It is the angle between the orbitals bearing the shared pair of electrons or the bonded electrons around the central atom. In order to understand this, I will give one example. Say water molecule H2O. There is one atom of oxygen and 2 atoms of hydrogen. Normally, when we represent water molecule, we represent it as HOH, oxygen in the center and 2 hydrogen atoms on either side of this oxygen atom. This gives the idea that the angle between the bonded pair of electrons around the central atom is oxygen atom, is equal to 180 degrees. And it looks as if the molecule has a linear shape, that is in the form of a straight line. But spectroscopy has helped us, it has allowed us to calculate the angle between these 2 bonds. Of course, the angle between any bond. We are referring to water molecule. And it has been found that it is much less than 180 degrees. I will give 2 diagrams here so that you can understand it better. This is the oxygen atom, which is the central atom. And these are the 2 hydrogen atoms. And this form the shared pair of electrons. Please see the diagram. What does the definition tell? Definition says that it is the angle between the valence shell bearing the bonded pair of electrons. For hydrogen atom, there is only one shell and that is the valence shell. It has only one electron. For oxygen atom, I have shown its valence shell with 6 electrons in it, shown in blue color. For oxygen, 2 more electrons are present in the inner shell. That is not shown here, only the valence shell is shown. I have shown the 2 lone pairs of oxygen. So, as per definition, it is the angle between these shared pair of electrons which is called the bond angle, and it has been measured to be equal to 104.5 degrees. Angle is measured in degrees, you know that. So, when we represent this diagrammatically, how will it look like? Look at the other diagram. Central oxygen atom with 2 lone pairs of electrons, and the shared pair of electrons form one single bond each with the 2 hydrogen atoms. The angle between these 2 bonds is 104.5 degrees. That is, the bond angle for water is 104.5 degrees. Representing it as HOH in a straight line is wrong. It has to be represented as is shown in figure number 2. I hope it is clear. Let us pass on to the third bond parameter, that is bond enthalpy. Enthalpy, you know, is the energy change. We will consider a few examples in detail in order to understand the significance of this bond parameter. First, we will consider homonuclear diatomic molecule having single bond. For example, hydrogen molecule H2. H single bond H. Bond enthalpy is the change in energy accompanying the breaking of 1 mole of bond of a substance in gaseous state. Consider 1 mole of hydrogen gas. It absorbs sufficient energy and breaks up into atomic hydrogen also in gaseous state. The energy that it absorbs has to be supplied from outside, and the energy that is absorbed by 1 mole of the substance to break the bond is what you call molar bond enthalpy. So when you write this equation, you have to add up delta A H, then the symbol for molar, that is a circle with a line that represents molar. And what is the value? 435.8 kilojoules per mole. Let me explain. Why do substances enter into bonding? It is only to make them stable. And how are they made stable? By losing energy. Less the energy, more the stability. So when bond is formed, that is when hydrogen atoms in the gaseous state combine to form or get bonded up to form 1 mole of hydrogen in the gaseous state, then how much energy is given out? 435.8 kilojoules of energy is released. Now that energy has to be supplied in order to help this 1 mole of hydrogen gas to break up into atomic hydrogen in gaseous state. So that is what happens here. What has been given out has to be supplied. Now let us consider homonuclear molecules with double bond and triple bond. For double bond, we will consider oxygen. 1 mole of oxygen gas absorbs sufficient energy in order to break up into atomic oxygen in the gaseous state. And the energy that is absorbed is its molar bond enthalpy. And in the case of oxygen, it has been found to be equal to 498 kilojoules per mole. So when you come to double bond, you can compare between the single bond and the double bond. You can find that more energy has to be supplied to break up double bond when compared with single bond. Molar bond enthalpy for oxygen is greater than that for hydrogen because oxygen has double bond. Now we will consider homonuclear molecules with triple bond. N2, N triple bond N. 1 mole of nitrogen in the gaseous state absorbs sufficient energy and gets split up into atomic gaseous nitrogen. And the energy that is consumed is its molar bond enthalpy. And that is equal to 946 kilojoules per mole. Here you find that for the triple bond, the molar bond enthalpy is greater than molar enthalpy for breaking double bond, greater than molar enthalpy for breaking single bond. We have considered 3 cases now. Hydrogen with single bond, oxygen with double bond, and nitrogen with triple bond. Molar bond enthalpy for nitrogen is the greatest. The molar bond enthalpy increases from hydrogen through oxygen to nitrogen. Greater the molar bond enthalpy, the stronger the bond, and the smaller or shorter the bond length. I shall note the point there. Please note it. Is that okay? And we find that accordingly the bond enthalpy also increases. Therefore, the bond enthalpy suggests how strong the bond is. Now let us take up another example, heteronuclear molecule, of course with single bond only. Example, hydrogen chloride, H single bond Cl. 1 mole of hydrogen chloride gas absorbs sufficient amount of energy and gets broken up into gaseous atomic hydrogen and gaseous atomic chlorine. And the amount of energy absorbed is the molar bond enthalpy for hydrogen chloride, and that is equal to 431 kilojoules per mole. So here you find for a heteronuclear molecule with single bond, the molar bond enthalpy is lower than the molar enthalpy for homonuclear molecule. So here we have considered only diatomic molecules. Now we will consider the molar bond enthalpy for heteronuclear polyatomic molecules. We will consider water as an example. H2O, you have to represent the central atom oxygen and then represent 2 hydrogen atoms at an angle. You have to also show the 2 lone pairs. I have not shown it here. Though hydrogen is attached to the oxygen by single bonds each, the energy required to break these 2 bonds is different. 1 mole of gaseous water first absorbs some amount of energy and break up 1 hydrogen atom from it plus 1 OH group, all in gaseous state. And the molar enthalpy number 1, that is for breaking the first bond, has been found to be 502 kilojoules per mole. The next step, 1 mole of gaseous OH group now absorbs further energy and breaks up into gaseous oxygen and gaseous hydrogen, and molar bond enthalpy 2, that is for breaking the second bond. The molar bond enthalpy is less. Why it is so? It is because of the change in the chemical environment after the first bond has been broken. So in the case of polyatomic molecules, the average bond enthalpy is taken. How is it calculated? The total molar enthalpy for all the bonds is first calculated and it is added up. Then that quantity is divided by the total number of bonds. Then that gives mean molar bond enthalpy. Mean means average. So in the case of water, we have to add up 2 quantities, 502 plus 427. Then divide it by 2 because we have considered 2 bonds there. And the mean value becomes 464.5 kilojoules per mole. We have considered 5 examples for molar bond enthalpy. Now we will take up the 4th one, that is bond order. It is a very simple topic. Bond order is another bond parameter or bond feature. It is a very simple topic. We already know the term bond number. When we discuss Lewis covalent bond, we have discussed bond number. So for single bond, the bond number is 1. Say for example, hydrogen. For double bond, bond number is 2. Example, oxygen. For triple bond, bond number is 3. Example, nitrogen. Here, instead of bond number, when we come to bond parameters, instead of using the term bond number, we use the term bond order. So, the bond order of hydrogen is 1, bond order of oxygen is 2, bond order of nitrogen is 3. So, the bond order increases progressively from hydrogen to nitrogen. We have seen that molar bond enthalpy increases from single bond through double bond to triple bond. And here we find that the bond order also increases from single bond through double bond to triple bond. Bond enthalpy is the greatest for nitrogen, greater than oxygen, greater than hydrogen. Now let us take up isoelectronic species. What are isoelectronic species? Molecules and ions having the same number of electrons. They are called isoelectronic species. We will consider the first example, fluorine molecule and peroxide ion, O2, 2 minus. In both of them, there are 18 electrons. Isoelectronic species have the same bond order. The bond order in fluorine is easy to find out. It has a single bond, so the bond order is 1. So, from that we can also guess that for O2, 2 minus, the bond order is 1. That means there is a single bond between these two oxygen atoms. You may try drawing the Lewis electron dot diagram for O2, 2 minus. Find out whether you can do. If you find it difficult, comment in the comment box. Then I will do one video for that. Okay. Atomic number of fluorine is 9. So, 2 atoms of fluorine means 9 plus 9, 18 electrons. Oxygen, atomic number is 8. So, 8 plus 8 is 16 plus 2 extra electrons. That makes it 18. So, they are isoelectronic species. Next example, nitrogen N2, carbon monoxide and NO positive ion. As they are isoelectronic species, that is, as they have the same number of electrons in them, their bond order also will be the same. It can be easily guessed from that of nitrogen. For nitrogen, the bond order is 3 because it is triple bond, the molecule is triple bonded. So, for carbon monoxide and NO 1 plus, there are 3 bonds. The bond order is 3. Let us check up whether they are isoelectronic species. For nitrogen, atomic number is 7. N2 means there are 2 atoms. So, 7 plus 7 is 14. Now, coming to carbon monoxide, carbon atomic number 6, oxygen atomic number 8, 8 plus 6 plus 8, that also is 14. Now, you come to NO plus. Plus means it is having 1 electron less. So, for nitrogen it is 7, for oxygen it is 8. So, it has 1 positive charge. Therefore, from total you have to deduct 1 electron. 8 plus 7, that is equal to 15, but you have to deduct 1. Then it becomes 14. NO positive ion also has 14 electrons. So, all of them are isoelectronic. This is how you find out which of the given species are isoelectronic. I hope it is clear. The bond order of nitrogen is 3. So, from that we understand the bond order of carbon monoxide and NO plus is also 3. Now, we will see how these 4 quantities, that is, these 4 bond parameters which we have discussed in 2 different videos are related. Greater the bond order, greater the bond enthalpy, but less the bond length, and greater the strength of the bond. This point also may be remembered. Do not forget to subscribe my channel. Thank you very much. We will meet in the next video with another important topic like this. Till then, bye. Take care.